Welcome back to High School Physics Explained. My name is Paul, and in this particular video I'm going to go through another HSC question, and in this case it's the question 27 from the 2014 HSC paper. So if you have an opportunity as I go through this question, I will pause briefly, is to do the question as you go along, and then I'll explain how to mark it and how to get a correct answer. This question actually deals predominantly with the topic on space, so particularly looking at orbital motion and about the slingshot effect and also gravitational potential energy. So let's get straight into question 27. So question 27 talks about, in this case, a space probe is being launched from Earth and set into Neptune. You have to explain using physics principles why the space probe takes this path instead of traveling directly to Neptune. Why does it not just do that? Well, we need to first of all examine the diagram very closely. And one of the first things you need to understand in understanding the diagram is that there is actually two, if you could argue, three components to the diagram. Let me get rid of that arrow. First of all, there's the actual launch of the space probe, and then it's put into orbit. It's easy to overlook this. Okay, yes, this part is very important, and most people already know that this is actually the slingshot effect, but let's also see that it actually goes into orbit first. So you need to talk about these parts, that is, that it goes into orbit and then it goes off onto Neptune. But it's an explain question. So it's cause and effect. So what's the reason by putting it into orbit? What's the effect? Okay, so we obviously have the launch, okay, and then it's placed into an orbit. Okay, and why is that placed into an orbit? Well, of course, there's a couple of reasons why you could give to that. First of all, by actually placing it into orbit, you can have the rocket leave that orbit at an opportune time. So once it's in orbit and in stable orbit, basically NASA or whoever's launching it can clearly decide when to launch it at the most opportune time to cause a slingshot effect, because obviously the timing is determined by the positions of the planets. So you could say that there's flexibility, okay, in terms of actually when putting it out into orbit. You can talk about the fact of, you could have multiple missions, you could have a particular payload, and therefore by putting it in orbit, it makes it actually a little bit easier in terms of launching it out into deeper space. But clearly you need to provide a strong physics reason as to why it may be put into orbit. And then of course it goes into the slingshot effect. And of course, the slingshot effect is using the gravitational attraction of the various planets to alter the velocity and the direction of my space probe. So again, the slingshot is, what we're doing is, of course, we're using the gravitation of the various planets, right? The acceleration due to gravities to alter the course. So we've got the direction change, right? Why would you do that? Okay, and of course the speed, and of course that is all about conserving fuel. Okay, because there's not writing here, we are conserving fuel, because ultimately we're relying here on first law principles, Newton's first law, in order that it gets out into Neptune. So that would basically give you 3 marks. So now let's look at question part B. So here is a calculation, and in this case we're asked to find basically the period of the orbit. So as you read this question, again I want to pause for a brief moment, and I'd like you to actually do the question. So how would you interpret this question? Now it's placed in orbit of an altitude of 188 kilometers. That's the first thing you need to note. When you see the altitude, you know that we are not talking about the radius here. This is simply the height of the space probe above the Earth's surface. So when you determine any radius, you know automatically it's not just 188 kilometers. It's 188 kilometers plus the radius of the Earth. Now it's asking you now to calculate the period of this orbit. As soon as you think of period, my hope, of course, it's only worth 2 marks, is that you're thinking of Kepler's third law. And Kepler's third law, of course, states that the ratio of the r cubed over the period squared is a constant. And of course, that constant happens to be gm over 4 pi squared. Okay, so knowing these are constants, and since we are already having the values for r cubed, you can clearly see how to solve this. Now here's a correct formula. Important tip, particularly for HSC purposes, although it's nice to rearrange this to get t being the subject, it is always good first to substitute into a correct equation. So first of all, we need to get the radius, and the radius, of course, is the sum of those two values. So we've got 6,380 kilometers plus another 188 kilometers, okay, giving a grand total of 6,568 kilometers. Okay, but of course that needs to be in SI units. So what we end up getting is having 6.568 by 10 to the power of 6 meters. And that's really important that you've got this as the actual radius. Now you can bypass this, of course, and you can go straight away and just substitute everything in. And what you do is you say 6,380 plus 188. You put brackets around it and multiply it by 10 to the power of 3. So we know that we have the correct SI units right away there. So we've got this, here's our r. Of course, we have to cube this, and then over here we have t squared, and of course t we need. And then over on the other side we have 6.67 by 10 to the power of negative 11. Now, the mass of the Earth in 2 significant digits is 6 by 10 to the power of 24. And then we put that over 4 pi squared. I've now substituted into a correct equation. And then, if I now rearrange this, I get this. T equals the square root of 6,380 plus 188. Of course, that's all by 10 to the power of 3, correct SI units. Okay. That, of course, is cubed, and that is multiplied by 4 pi squared up top, and then the bottom we have 6.67 by 10 to the power of negative 11 times 6.0 by 10 to the power of 24, and that, of course, equals 5,286 seconds. And if you would like, that can be converted to 88.11 minutes. Okay, so for 2 marks, correct substitution and then correct rearrangement to give you your value. Where you could potentially lose marks, you're going to be watchful of, is that you've forgotten to add the 188 to the 6,380. Or, which is another common mistake, is you forget to multiply this by 10 to the power of 3 because the unit here is kilometers and the unit needs to be in meters. So you've got to be careful that you always are using SI units. And so now let's have a look at part C. In this case, this question is about gravitational potential energy. And it's asking you, what does the axis, or what does a graph show in terms of gravitational potential energy for the space probe as it takes off in 10 minutes and then stays in orbit? So before you look on, you need to make sure you understand the nature of gravitational potential energy. Gravitational potential energy is always such that change is always where you've got work done in order to move it from an infinite point to a position above the Earth. That is, the gravitational potential energy is 0 at an infinite point. But if I lift something up and I'm moving it towards that infinite point, we are obviously gaining gravitational potential energy. And so therefore, if I am going to be increasing gravitational potential energy, and yet I'm moving to a point that ultimately has a zero value, it means that the gravitational potential energy at any point is always a negative. And therefore, the graph for that situation, for a general gravitational potential energy, is always below the axis and tends to zero like this, where this is infinity and this is equal to GPE. So that's what we understand. But we now have to apply that understanding to this situation. Well, clearly it is launched and then it stays in orbit, which means its position stays the same, which means its gravitational potential energy is going to remain the same. It's not going to change at all. And so really from a particular point in time, maybe from, let's say, in this case, after 10 minutes, you're going to expect it to be horizontal like this. It's not going to change. But of course, prior to that, it will need to be increasing. So it's going to curve down like this. And so that's what the graph should look like. We have, first of all, it's always on the negative side. We have this curve, this hyperbola over here, but because it is going in orbit, then you need to understand it is a constant value from there on in. I hope that helps you in answering question 27 from the 2014 HSC paper. Thank you.